Hello everyone, good morning. Today our group will be talking about the applications of linear algebra in cryptography. My name is Arnavuddin. I'm Sadir.
And I'm Rafi.
So Rafi will get us started.
So as our topic is cryptography, I'm going to start with defining what cryptography is. Cryptography is the study of encoding and decoding secret messages. These secret messages are then called ciphers. The process of encoding a message is called enciphering, and the process of decoding a message is called deciphering. Next slide. There are different methods where we can encipher a message. The first one that we're going to talk about is substitution cipher. A substitution cipher would be a type of ciphering where we would just replace an alphabet with another alphabet. For example, if we see this example, A becomes D, B becomes E, C becomes F, D becomes G. This is a very simple example of enciphering where we just shift each letter with 3 letters to the right. This example of ciphering is called Caesar cipher. There's another type of substitution cipher which is called random ciphering or random substitution with ciphering, where A can become K and B can become N and C can become A. But the problem with substitution ciphering is that it preserves frequency. For example, it is very likely that each letter is just shifted 3 to the right. And the problem with that is using the statistical methods and formulas, we can decode this cipher. Let's take a look at this example, IFMMPXPSME. This is a cipher, an encoded message. Let's try to solve this. So this is a very simple, as we know that this is the substitution ciphering. We can just, what has been done here is that each letter has been shifted to the right, and if we shift these letters to the one letter to the left, we get our secret message, which is hello world. Thank you.
As Rafi just explained, there is a huge weakness when it comes to using Caesar ciphers. That is, they preserve the frequency of individual letters. Instead of Caesar ciphers, we can instead turn to Hill ciphers, which are a stronger form of encryption. Hill ciphers use an encrypting matrix to turn plain text into ciphertext, and they turn a group of letters instead of a single letter at a time. This type of encryption is called a polygraphic system. It assigns the letters of the alphabet numeric values, like A equals 1, B equals 2, and so on, and then it turns the plain text into a vector, like this. The length of the vector depends on the size of the Hill cipher, and we have an according encrypting matrix, and we use the matrix product to compute the ciphertext. Let's look at an example of Hill ciphers. So over here, our plain text is I am hiding. As we're using a Hill 2 cipher, our matrix is going to be a 2 by 2 matrix, and we're going to split our plain text into groups of 2 letters. So we have IA, MH, ID, IN, and GG. The last G here is a dummy letter. It's made to ensure that all the letters have a pair. We can turn these letters down into numerical values using the system we introduced in the last slide. And to encipher these pairs, we multiply them with the matrix that we have. This gives us a new vector, which is also 2 components, and we can turn these numbers back into the alphabet and get 2 new letters. These are our ciphertext. If we do the same thing for all of the pairs, we get our final ciphertext, which is usually represented without any white spaces. If we tried enciphering all the pairs on the last slide, we would see that we had a small issue. For the second pair, which is MH, if we represented MH as a vector and computed it using the matrix product, we would get 29 and 24. This is a problem because 29 is a number that has no representative alphabet in the English language. And to solve this problem, when we have any number that's bigger than 26, we wrap around from the beginning of the alphabet. So 29 goes to 0. So when we're done with 26, we go back to 0 and then have 1, 2, 3. And so M becomes C. That's why our output for MH becomes CX. So the wrapping around operation that we introduced in the last slide, there's a name for that, which is called a modulus. Mathematically, this is denoted by A equals B mod M. Modulus can be understood easily by a similar and hopefully more familiar concept, that is the remainder. We saw that 29 was wrapped around 26 to become 3, and if we represent this in terms of remainder terms, we have 29 equals 26 times 1 plus 3. 29 is the dividend, 26 the divisor, 1 the quotient, and 3 here is the remainder. 3 is the result also of the modulus operation that we got, which shows that modulus equals the remainder.
So which modulus is also reciprocal modulus? Basically, we want to find such an x that 3x is equal to 1 if we mod it 26. So to do this, the obvious answer is just if we mod 27 by 26, then we'd get 1. So then we have to determine how do we get to 27. We could just do 3 times 9, such that the reciprocal of 3 would be 9. This is for other things as well, like not the modulus of 9. The reciprocal of 9 would also be 3. They're in pairs. However, there are some numbers that don't have reciprocals, like 4, because they can't really find such a value, such an x, where it equal them. And it's because they don't share common prime numbers. So if you wanted to decode a health cipher, we'd want to first represent our plain text, our cipher text, by doing the multiplication of A times the plain text cipher times the plain text vector, and then we would get the plain text cipher by doing the inverse of A onto C. So if you want to do this, we could just do, it's pretty simple, just get the inverse of A. So we already computed it for you. So 5, 6, 2, 3, inverse is 124, A19. So as an exercise, we had this little code, and now you can decipher it using your new knowledge that it's a two health cipher and knowing A. So this is like the computation for it. You can see again how we have very large numbers. We just mod it though, such that we get actual numbers we can use. And then if we convert it back to its alphabetical equivalence, we would get strike now. So if you wanted to determine the deciphering matrix, it's a bit hard. It depends on how much information we actually have. So I mean, this whole entire thing is about security and such. So for example, let's say we have this ciphertext. We don't know anything about it. It could be a health cipher, it could not be a health cipher, but let's say it is a health cipher. We still don't know what cipher level it is. If we know it's a 2 cipher, we still don't have any clue as to what 4 entries it could be, but we could easily just brute force that one. If we had a 3 health cipher, it would be 9 unknown entries, which would be way too big to brute force. Also, dictionaries are possible options, but it's also kind of hard to determine what's the right text, since we don't have a rigorous one-to-one. So there is actually an algorithm as to how to find the deciphering matrix. Basically, if we know some information, let's say we know it's a HEL2 cipher and that the first 2 pairs are equal to DE and AR, then we can find it such that we make a matrix P that is a transpose of the plaintext vectors, and the matrix C such that it's a transpose of the ciphertext. And then basically we would augment C to P, and then the row operations that we do onto C to convert it to the identity, we do onto P. That will give us the inverse of the transpose of the cipher matrix A. Then after that, we can just take the transpose of that matrix and we'll get the inverse matrix A.